Grazie, Presidente Antonelli, Presidente Parisi, Roberto, Giorgio, distinguished colleagues. It's a true pleasure and honor to speak here. I must say I'm very jealous of this grande palazzo. We can't compete at all with our little house at the Leopoldina. It's almost an embarrassment. It's my first time in Rome. I did a 2-hour walk this morning from 8 to 10 after breakfast, and I think I do have a new favorite city on planet Earth. So it's a real pleasure to be here at the Lincei, which we consider probably amongst those few but most important national academies on planet Earth, which we feel are true partner academies. And with my rudimentary Italian, you've mentioned the G7 process, where we've worked very closely together. It was last year Germany, this year Japan, next year it's going to be Italy. And we continue this very, very trustful collaboration. What I plan to do now in those, I think I was given 45 minutes, is that correct, in this presentation? It has two aspects. It's describe a little bit what we do at the Leopoldina and also what we've changed in our style of working at the Leopoldina given the needs during the pandemic as one of the crises, and you will see it'll come out in the formats. Speed was a very important aspect. So the main criticism we had as a Leopoldina, but probably as a scientific community as a whole, from society, including politics, that, well, you have this in-depth knowledge, but you're absolutely lame. When there is a discussion in German TV on what could be a science-related topic, and you come with a 200-page statement, or 1 year later, it's not so useful. So we've changed some of our formats to address the speed, the need of speed in the pandemic, and that led to some impact which we had as a Leopoldina. Most people liked it, some of course didn't, but I try to explain a little bit on what we have done. And then there is a second part of my talk in the middle, which is trying to explain as a climate scientist. It will have a less pompous format based on ice ages, the urgency of acting on the climate system. That's probably an attempt to make you understand why I do what I do as a probably somewhat too young person to be the president of a national academy. So this is somewhat the outline. I can't see the slides unfortunately here, but that's fine. That's what matters. Is first a very banal concept of crisis. Then what I said, there probably, this is a discussion we should have amongst the National Academy, probably then a new age, the need for a difference in science-based advice, where I think we are as academies are extremely well suited. And then I do my climate spiel in the middle to come then what we've done and recommended on for example, which we think is very important, the G7 level and some of the European formats, which we also work closely together with you, but basically trying to have, for example, with the example of genome editing, future of agriculture, a discussion with Brussels at the EU level, and then some brief conclusions. So what is here is a short outline. I come from the lower end, basically on the right side, which is climate. This is great. And then does it work like? Okay. But here. So I come from the lower end here, the climate crisis. This is what I do since 30 years, ever since I was a student, particularly as a PhD student. But the world has become very, very complex, as we all appreciate. So we are now in a situation that we have unexpected crisis, something which we would have never thought that there's a war in Europe. On Monday, I was in Ukraine with our Federal Minister of Science. I got invited, and I met our wonderful colleague, Anatoly Zagorodny, the president of the Ukrainian Academy. Some of you have met him in Berlin at the G7 meeting. I mean, it's so touching to see how the Ukrainians, also our colleagues at the Academy, at the universities, we've been at Kiev universities, fight for their independence. They rather die than to become, under whatever would be a Russian leadership. So I recommend everyone, when this is probably a little safer, to go to see and support basically our wonderful colleagues there in Kiev. So this is probably one of the unexpected aspects which we would have never expected to happen in Europe in the 21st century. We just had this week disruptive effects. I know this as an earth scientist. There was a huge earthquake which we've all seen in Turkey and Syria also, with more than at the moment 20,000 deaths. It'll be more. So we do have, of course, those nonlinear escalations which we, from natural disasters to very sincere political crisis we're facing. So there is very often what we call a cascading crisis, the perfect storm, the multiple crisis, right? From a pandemic into a war, into now a situation in Turkey, in Syria, which all impacts us at the very huge magnitude. So what I and I think we think some of those crises do need and deserve rational decisions. The decisions have to be always made by our politicians, that's obvious. But I changed the word must to the word should, being a little more realistic than some of my excellent reference at the Academy. Management and response to crisis should be and needs to be very often scientifically grounded. And if we think and go just in one slide back, I don't want to talk about the pandemic, which is gratefully pretty much over. When we think the role of science in the pandemic, it's been outstanding, right? From identifying the transmission, the role of aerosols, to basically producing a vaccination. I'm a Max Planck director in Mainz, and my family lives there with the BioNTech team, that wonderful Turkish couple, Özlem Türeci and Uğur Şahin, with Christoph Huber as the senior guy, at basically no time, 8 months, right? They've developed what nobody would have probably put a euro on a complete new technology, based, and this is at my heart, based on 20 years of fundamental research, a vaccine, right? It would have been not possible without basically those, at the end, oncologists working at that high level on mRNA techniques, right? So this is of course what we do from basic research to new technologies. The vaccines is the best possible example. But what we also have been engaged here at for example, the Leopoldina, is science-based policy advice, and we can communicate to different groups in society, including politics. In the pandemic, it was fairly easy for us to have that communication, as we had with Angela Merkel, the German Chancellor, who happened to be a physicist. And she perfectly well understood our world. She knew what a publication record means, and she knew the difference between an opinion and in-depth knowledge, which I think is very often difficult, particularly for people who have not introduced to our world. So that was a fairly easy communication. Still, the pandemic is a no-win situation, and is what it is. But I think at the end, given the combination of measures we had and the vaccinations, at the end it could have been much worse. So I felt that we've played our role. Politics did what politics could do. It was different in the different countries at different times with different needs. So I think we've done that. What we've learned, this is what I said at the beginning, science-based advice is not static. It needs regular responsive updating. And there, in the pandemic, the speed was a difference. Once we wrote a statement in a week, right? Usually we take a couple of months to a couple of years. The longest statement the Leopoldina had was a long report on the natural science thinking of Goethe. It took 70 years, right? So from 70 years as one extreme to 7 days, that's basically the bandwidth which we've worked on. And given the in-depth knowledge of us, basically the members of the Leopoldina, and we also engaged younger colleagues, particularly those in the early 40s who are probably yet too young to become Leopoldina members, but are clearly a top-level scientist. We were able to produce this, I would say, without any major mistakes. Some people didn't like that, but basically motivated from our medical class. The Leopoldina has 4 classes. The biggest one is medicine. That's the origin of the academy. And when 5 of the biggest clinic chefs call someone like me as the president and say, do something, otherwise people die on the parking lot, it's time for action. And we've learned how to do that. So I think this is the other extreme, and where we've changed somehow our way of working. So I do believe that national academies, we are amongst the most authoritative voices in the scientific community. And I say we can basically, if a working group of, let's say, 25 or 30 of us on national level, or what we do at the G7 level, find a consensus in a completely multidisciplinary, transdisciplinary working group, it's almost like a scientific, an MOT, as the TÜV, the German, we call it. Usually there's nothing stupid written down, right? And in those worlds where everything is done in talk shows, I think this is a good counterpart that we have, and we, I think, have the duty to also do this in due time. That's very important, right? So what we've done is we have those new way of working. Of course, we have always had our statements. We have what we call now focus group, continuous groups. There are 4 focus groups, one in climate and energy, a medical group, one in biodiversity, and one for digitalization, where we have, they have to meet once a month. Right? So there's continuous advice and monitoring, and then it doesn't need to be all that ad hoc. They can basically, out of their work, this is usually 12 people, 12 members, and they can immediately use also the other format to bring up a statement. What we have been not so good, I feel, and have to still get better, is the anticipation of things we should work on, we could do when what addresses the work academy. And then we've learned how we can do rapid response advice. That it's still difficult. It's when I became president, many members said, well, I have no time, I'm too busy, and I have better things to do than to work extra, 2 weeks very intensively for the Leopoldina. The pleasant thing for me as president, that doesn't happen anymore. And Roberto, when, the golden rule is, and George, if the president calls, the president doesn't have to beg. So at the moment we have 100% participation if we, or I engage myself into the process. So that's the very good outcome of the pandemic, because the members, even the most noble members we have, understand that in a working group, in a consensus, it's a different kind of impact, even the highest level members we have. I look at George. One of my heroes was always at my institute. He died, unfortunately, 2 years ago, Paul Crutzen, with the ozone chemistry, where he got the Nobel Prize for, and the Anthropocene concept. And Paul, of course, always understood that. I'm a marine geologist. By getting along on ships, you cannot work different than a team player. And I think we've all understood that at the Leopoldina. I'm very pleased about that development, that people really participate and do work hard and for a concentrated process. So here's what I've already mentioned. I can go quickly through. We have at the moment those work format, the focus groups, who work continuously on ongoing processes and problems of kind of obvious discussions we have our scientific commissions. They work on much longer term aspects, right? We have 2 medical commissions, one for ongoing things and one for natural sciences in medicine, for example, which will not go away as an educational process. It's just one example. And then any member can basically propose a working group and get help, get groups together, and this can be relevant for policy, but it can be just also an academic process in the small class, for example, of the humanities we're having with an ethics group and so on. So this, of course, is all happening. The new aspect is basically the speed we got out of here and in some of the formats we've implemented. If I look at Germany, there's a huge amount of lobbying going on. There's just so many pressure and peer groups and lobby groups there in Berlin, and I think it's really hard for politics to understand, who to listen to, and most people do what they do also, which is fine in the free market, in a social market society, to earn money, right? We don't do that, and that's why I absolutely refuse to see ourselves as a group of lobbyists, right? Because we have no financial interest. And then we have other peer groups who do very good work. They call it like a board. Germany has all sorts of rats and councils, basically, an ethics council and a hydrogen council. There are dozens of councils. What they do, and if politics wants advice, they get together, the parliament and the government, and then each party can identify their experts and put into a council. Then they're given a reasonable amount of independence. But all the experts are put in by the political parties. So you kind of know what the outcome is, right? For your experts, which the right wings do and the left wings do, and everyone has their scientists, and that won't work very often very well. One of the few completely independent groups who do get the ear from time to time at high-level politics is the National Academy of Science, us, the Leopoldina, and we are completely independent. We had one federal minister who had to change a law because of me, because he wanted to give me an order and put that into a law. I said, no, change the law, otherwise I put you publicly on stage. So he did change the law, right? And independence. That's the key aspect on the way we work. Sure, we get our money, 80% from the federal government, 20% from the state of Sachsen-Anhalt, but still the most important thing, and there's probably no other way in the German funding system, is that we cannot be touched politically by telling us what we have to do. Of course we interact, of course we accept invitations and are always available for advice, but we're not told what we write, in which group we write. This is entirely a decision of the Leopoldina. The Board of Presidents basically makes this group up. The ad hoc groups are in the responsibility of the president, and it's completely independent. So this is probably the key aspect here, is independent science-based advice, right? So the decisions on the topics come from us. The independence is the backbone we are having. We also have a free choice of partner organizations. It's also very important. I mean, we are not completely autistic. The G7 is one of the given processes, but it's the highest level process where the national academies basically work together. But also nationally, we, for example, had an excellent paper on climate change, which was the Council of Sustainability, which was a very interesting experience, because it's also 50% politicians in there, and it was a success, but I won't do it again. Right? That's also an interesting aspect, right? And of course, we do have compliance and peer review mechanisms, even for the fast statements in place. So if you write a paper in 7 days, it's up to the president. Said, look, we will have a draft on Friday, and then I need 3 independent top scholars for Saturday, right? They would give me those 6 hours, which they usually give me in 8 weeks. They said, you have time on Saturday? I want a tough review, but I need it on Saturday. People agree to do that. So the quality assurance is there. It's just basically our job to make our colleagues work a little faster. In the pandemic it worked, it's become more difficult. So I switch over now and try to explain my motivation as a climate scientist. So what we do now, coming from the policy advice, quickly to the science part of my presentation. Roberto said I'm basically a marine geologist and oceanographer, a paleoclimatologist. And what I try to do now is to explain the urgency on the climate problem in a pure scientific sense as an Earth scientist. What I do in 15 minutes is a run-through to Earth's history and try to explain Paul Crutzen's Anthropocene point, basically looking at the last 60 million years. That sounds probably per se a little exotic, but I give it an attempt. The probably most important curve we have to understand that we have this man-made impact on the atmosphere is what we call the Keeling curve. Charles David Keeling, now his son Ralph at Scripps, have this Mauna Loa observatory. You have all seen the curve. The last reading was, or that was from last Friday. We are now at 420 ppm, which we've been over a year ago. I'm born in 1968. There the atmospheric CO2 concentration, and I don't feel particularly old, was 320 ppm. So in my lifetime, the atmosphere has changed by 100 ppm. And we could say, so what? I hear very often as a paleoclimatologist, well, it changed, the climate has always changed in Earth's history. So this is exactly the point I want to make, but the scale has completely changed, the time scale and the order of magnitude. So I'm going to run you quickly through and quickly try to explain how an ice age works and what that means. So here's basically what we've just seen, the Keeling curve. These are not the last 1,000 years. Then you go to the ice core measurements, and we do know that in the Holocene, the atmospheric CO2 concentration was something like 280, 290 ppm. And then it started to rise in the past century, and then Powell's point came, everything is gonna exponential, right? So now we are, this is a little bit of an outdated 10-year-old picture, but it's good to use old pictures, right? 10 years ago, it was 380 ppm. Now we are here at 422. This is very important. Without sinks, we would be at, that was 10 years ago, 535, at 550 ppm at the moment. The two biggest sinks are the ocean and the land biosphere by CO2 feeding. So the ocean is our very good friend. I will not speak about temperature very much. The ocean takes up 90% of the man-made temperature and about 25% of the man-made CO2. Acidifies, we've all seen that. If that would be the case, and the other half warms the atmosphere, we wouldn't be, we'll see this in a minute, not at 1.2 degrees global warming, it would be already at 2.5 degrees warming. So I try to explain quickly how the ocean does take up atmospheric CO2. I mean, the outcome we all know. We are here at 1.2 degree warming, and if we continue in a business as usual scenario, I did deliberately chose that the previous IPCC report, because I think the next one will be further up at the higher scale, we do have the possibility to increase the global temperature at the end of the century if we burn just everything which is cheap at the surface. Or at the moment, the numbers are at 4.5 to 5 degrees Celsius. It could go up to 6, right? It doesn't matter. I'm one of those who is working ever since we have that limit on the 2 degree policy limit. The 1.5 degree policy limit, which came out of Paris, because otherwise there would have been no signature, is gone. Right? We're at 1.2. We have 0.3 cooling by our aerosols, which is dirt in the atmosphere, so with a clean atmosphere, we are at 1.5, right? So this is also something hard for our politicians, particularly the Green Party, to understand. Robert Habeck comes sometimes to my office, he understands it, but politically he keeps up with the 1.5 degree Celsius argument. But we are basically there. 2 degrees we theoretically can reach. At the moment we are at something like a 3.8 degree track, as if we do as promised, but nobody keeps the promises yet. So it's not very good news. Let's go to the ocean. How does the ocean work? There's ocean circulation, there's temperature effects, and we can go through all of this. But what you see here are the ocean sinks and sources of CO2. And in principle, we do know from a water bottle, if you cool the ocean, you take up more CO2. But you see now at the Southern Ocean in the North Pacific, despite being the coolest parts of the ocean, they are now sources of CO2. The tropics are partially obvious, right? But I want to talk about those sources. So here's kind of the basic numbers, the global ocean uptake of CO2 is of those about 10 petagram or gigatons CO2 is 2.2, then you have natural release. So we have this big friend of the ocean who takes up a very significant amount of the man-made CO2. How does this work? So this is a picture of the ocean. Here's the Atlantic. This is the North Atlantic. This is 4.5 meter water depth. So these are sections through the global ocean. This is the Pacific. This is the Indian Ocean. This is the way ocean circulation works. You have North Atlantic deep water, which upwells in the Southern Ocean, goes down, and so on. The CO2 uptake I've just described happens here in the upper water column. This is the upper, let's say, 500 meters or so, where the man-made CO2 is taken up. Then comes a stratification of the ocean, which we call a thermocline. And then we have these very thin layers here. This is the weak part of basically the ocean for man-made CO2 impacts, which we call a halocline. This is there around the Southern Ocean, and there we will come to talk about it. Also a situation like this in the North Pacific. Right? So it's a shallow ocean which acidifies, which is not very good for any of those plants or animals up to corals who calcify, they dissolve. This is what we call ocean acidification. I will not talk about this. The bad news is for us in a way that the deep ocean, what's below, has 60 times more CO2. This is dissolved inorganic carbon. You can translate this to CO2. And this is the big storage of CO2, which controls, for example, ice ages. This is what I'm going to try to explain. The exchange valve is the Southern Ocean and the subarctic North Pacific. Right? If we change the physics of the ocean, that's basically where we exchange the CO2, which is stored in the deep ocean, to the atmosphere. And they are very simple physical mechanisms which are still at work, of course, today with man-made warming. I'll come to this. So what we do as paleoceanographers, we take drill ships, we drill cores, and I show you two examples, one from the Southern Ocean and one from the North Pacific. So what I show are something like 250 to 400 meter long sediment cores. This is wonderful technique of drill ships, comes from at the end the oil industry, which allows us to take those sediments. And I'm basically an isotope geochemist, and with those methods we can reconstruct for hundreds of thousands of years, for example, the ocean temperature, but also productivity, the biological pump aspects, in an incredible precision, so over 100,000 to millions of years. And so what I'm going to do is I compare some of those sediment cores to the second most important measurements we have in climate, which are the ice core records, which are direct measures of past CO2 back to 800,000 years ago, which we can do in Antarctica. It's the group in Grenoble, Jean Souzel, and the Bern group, who clearly make the best measurements, very precise there. These are the well-known ice core records. So this is now 800,000 years before present. This is today. These are the ice age cycles, right? So in an ice age, the temperature on Antarctica is something like 10 to 12 degrees cooler than in an interglacial. Today, this is our interglacial, the Holocene, since about 10,000 years. The last ice age was 20,000 years. And then every, 100,000 years and 40,000 years and 23,000 years, you have those so-called Milankovitch cycles, which have big amplifiers. The two biggest amplifiers are the greenhouse gases. The most important one is CO2, the water cycle, methane, they go with that. And the albedo effect. I will not talk about the albedo effect today. It's about a 50-50 distribution, but without the amplifier, the carbon cycle, we wouldn't have those swings, which are the biggest swings in the climate system the Earth's history has probably ever seen. Right? In the last ice age, sea level was 120 meters below. Today, New York City was under 3 kilometers of ice. So what is a little wiggly line are just huge swings in the climate system. So the one thing is to measure them, the other one is to explain those 100 ppm, right? And this is, again, the 100 ppm, since I'm born, is exactly the difference between an ice age and an interglacial. What happened in 60 years or in 54 years, right, needs something like 3,000 to 6,000 years at those still at the end for the Earth's history fast glacial terminations, as we call them. Right? 54 years of my life is the same amplitude as something like, on average, 5,000 years at the glacial termination. Very different speed. Earth's history has never seen this at that speed. The same 100 ppm. It's also no doubt, this is the 420 ppm about scale. It needs to go a little further up even when you compare to the last 800,000 years here of the CO2 concentrations of the atmosphere. So it's also very, very clear that what happened the past 60 years has nothing to do with the natural carbon cycle of the last 800,000 years, right? If we continue as we do, we can go to 800 ppm theoretically also, if we consider the next century and just burn everything we have cheap to 1,800 ppm, right? I want to bring you now into, first explain those ice ages and then bring you into an Earth historic context, what that means. So the most fundamental aspect of ocean circulation is ocean salinity. What you see here is a map of the salinity of the ocean. The Atlantic is 1 per mil more saline than the Pacific. The North Pacific is the least saline with 1 per mil less than the Southern Ocean. And that drives Wally Broker's conveyor belt. Right? You've all seen the conveyor belt. That's the fundamental ocean circulation. So I will focus on the Southern Ocean and the core here and one in this blue part and explain the role of this basically freshwater cap here, which is best illustrated here, and the role when it goes stronger and when it disappears. When it goes stronger, you keep more CO2 stored in the deep ocean, but under warmer conditions, it can also disappear. And we can measure this in Earth's history with very simple measurements at the end. Right? So here's Africa, here's Antarctica. So we go now south of the polar front to a sediment core. It's from the ocean drilling program called 1094. It's the best core we have collected in the last 30 years of ocean history, drilling history in the Southern Ocean. So this is getting complicated. I try to keep it simple. So this is what you've seen before. This is the air temperature of Antarctica. This is the CO2 concentrations, again, the last 800,000 years. This is the simplest measurement we could do in one of those, let's call it a 300-meter long sediment core, ODP site 994. This is a color measurement. So you have 300-meter cores. You take basically from the supermarket a color scanner, costs probably a good one, 500 euros, and make a measurement every centimeter for those 300 cores. So what you see, you could see by eye that in the interglacials, the sediments have a lighter color. And the glacial, they have a darker color. So with a 500 euro instrument, you can quantify it, the photospectrometer. It doesn't get simpler. We've done tons of measurements in isotope geochemistry and whatever. You know, sometimes this is what my mathematicians and physicists who model tell me, you know Klaus, you know Mark Kane, right? What I can't see by eye with you guys, doofus geochemists, I don't believe anyway. So this is a color measurement where we see lighter color when CO2 goes up and temperature goes up. And that is a very simple explanation in biology. The organisms down there are diatoms. This is phytoplankton made of siliceous cells. Right? They are light in color. And the ice age is contrasted by mainly drop stones from icebergs. Colder, more icebergs, more clay minerals, and they're dark. Right? If you fly over the Labrador Sea, you see all those icebergs, and they're all very dirty, right? So this is the simple color distribution, which you can almost semi-quantify, right? So what it means when you go colder, or let's make it when you go warmer, you get more nutrients exposed to sunlight, just as we do in spring. Like these are plants. Those diatoms, those phytoplankton are plants. So when you have a lot of nutrients you expose to sunlight, you get a higher biological productivity. The problem is in winter, there is no sunlight. So the more you expose, the more you outgas from the deep ocean to the atmosphere. We call this the efficiency of the biological pump. So it's at the end a very simple process, which we understand well, which we can measure. That's basically at least 60 ppm out of the 100. The other one is another process. It's iron fertilization in the subantarctic to basically explain the 100 ppm CO2 change, which we measure in the ice cores. This is the sea level change, which we can with other measures. So this basically is 30 years of work of a huge amount of wonderful scientists, probably led by Wally Broker, Nick Shackleton, and some of those members of the academies. So you would say, well, why do we bother with an ice age? The world gets warmer. And this is probably the time interval I spent most of my time on ever since my PhD, this is when we have to go back 5 million years ago. And there was a time before we had those big glacial cycles, right? This is 2.7 million years ago and previously. The Earth has seen many glaciations in the Ordovician, the Permo-Carboniferous, the Southern Hemisphere glaciation since 36 million years ago. But that we have a bipolar glaciation is only happening since 2.7 million years ago. So it's a complete unique state, the very vulnerable state of the climate system, where we have some leftover on Greenland, and then the big ice ages where Northern Europe and the Laurentide ice sheets filled the Northern Hemisphere. In the Pliocene, there was no ice on the Northern Hemisphere. It's called the Pliocene warm period. We had a 400 to 450 ppm CO2 world. The world was 2 to 3 degrees warmer. No ice in the Northern Hemisphere. Biggest transition in Earth's history, with a little wiggly line. So the Pliocene is a very interesting period as an analog where the world looked exactly the same, but the ocean was fundamentally different. And I just show you one example of exactly the same, the change in the biological pump. Now from an example up here of Kamchatka, the Southern Ocean does exactly the same. So we look at basically diatom productivity over the last 5 or 6 million years ago. That was my PhD thesis. Actually, my advisor wanted me to fail this for a very stupid explanation, which was at the end the claim to one of the things which I've done useful. You see, this is the onset of Northern Hemisphere glaciation 2.7 million years ago. These are the ice ages. And what we've observed up there is a very abrupt drop, 100 years, where the biological productivity dropped by a factor of 5. So what I proposed is that, then it was all in vogue to have a conveyor belt and whatever, but that wouldn't work with such rapid transitions. That just put down the halocline, which drives all the polar ocean circulation today. And this is a very simple way of explaining that drop. But it has huge implications. So this is a short introduction to the oceanography there. This is what you've seen before. This is one of the key nutrients, it's nitrate. The highest nutrient and CO2 concentrations in the ocean are just below here. This is the Southern Ocean, this is the North Pacific. Sitting at the highest concentration the ocean has, below a very thin halocline. This is a freshwater cap. That's just a very dynamic cocktail glass, which is 120 meters thick. If you take that away, you can expose all the CO2 nutrients to the surface. There's winter, and then you can basically outgas, as there's no plans to bring it back to the deep ocean. And this is a very good explanation, as it happens on both hemispheres, to explain this 120, 150 ppm being Pliocene CO2 higher than an interglacial, and another 100 ppm when you strongly stratify both polar oceans in an ice age. So you could formulate, right? So this is the key here. This very thin, vulnerable surface of the ocean and the halocline, right? So this happens in the North Pacific, but it also happens in the Southern Ocean, which is the more important biological pump, the bigger. But the concert can easily explain, again, 100 ppm, right? What we have done now man-made, right? This is basically the 2-degree target. These are thresholds, which are in probably not this century, but introduced this century, which could then simply double up the man-made impact of CO2 when they are executed, right? So the Earth system, the ocean, is our big friend, but our concern is if we just now go too far above the 2 or 3 or even further, any of those ocean mechanisms will have feedbacks which would introduce more CO2 from the natural carbon cycle to the atmosphere. We call this a runaway heating in Earth's history, which has been seen before, right? So the simple scenario is when we look at the polar oceans, and this has been true in the Pliocene, ice ages, but also with man-made warming. In a warm climate scenario, there's no freshwater cap and an increased outgassing of CO2 in a biopump leak. In the cold climate scenario, we have the opposite. And the ocean doesn't care what warms the ocean. It could have been in Earth's history, a natural process coming from cooling, basically, or man-made warming. So these are what we call I don't like the word tipping points. I don't like that concept very much. I call this a climate threshold, the very serious climate thresholds, right? So if you look at it's old, but it's somewhat matters because this transition happened in 100 years. It's 2.7 million years ago. But when the system gets to those threshold type stages, we know much faster transitions if we look, for example, in the last ice age at Danskar-Oeschger cycles, which is mainly an on-off of the Gulf Stream. But this is about the time scale which it just could take, if we think of the Keeling curve, to be the second half of this century or next century where those basically mechanisms are introduced, and we could reverse these very, very big changes in ocean circulation. If we put this into modeling efforts, this is something we very often do with our colleagues at Princeton at the GFDL, right? Manabe was the key player. I have a joint graduate program with a colleague in Princeton where we get very student, just put in global warming and just ask the model the question, when does those halog lines disappear? Well, it spits out between 1 and 3 degree warming, which could be anthropogenic warming. It takes decades to a few centuries, which means no ice on Greenland. If you melt Greenland to 6 to 7 meters sea level elevation, in the Pliocene was more like 20 to 25 meters because the Western Arctic isn't as stable as we hope for. And probably the most important impact then, and I will not talk about it as my time is over, we describe this time, this is something, a word which Peter Molnar and Mark Kay and George Phelan have created, a permanent El Nino. So in the Pliocene there was a situation that, like an analog of an El Nino, which we'll expect basically this year to come, that the tropical rain belt moves south and it doesn't rain over much part of Asia. The Indian monsoon is weakened, the Chinese, the Southeast Asian monsoon is weakened. And if this happens in a permanent state, and you imagine that between those parts of the tropics and subtropics, if you think of the planet Earth, it rains more in the Indian Ocean and the Pacific where no people are living, and we lose big parts of the monsoon system, we will face the end of the century a situation where 2 to 3 billion people have just no place to live. It's too hot and ways too dry. So these are my big concerns on the thresholds where I do believe there is a huge urgency to address those problems. So one is the temperature. That's probably a marginal effect. But those changes in the hydrological cycle will fundamentally change the living possibilities in the tropics and subtropics. This is probably the bigger impact. So on a little bit of an almost cynical note, we go back 70 million years ago. All right? So we've seen the ice age is 200 ppm, CO2 300 ppm, the inner glacials. We are now at 420 ppm, which we've had last time in the Pliocene. It takes a little while. The ocean is sluggish and whatever, so it buffers many things we do, but that's the perspective. Here, this is the onset of southern hemisphere glaciation. Here's the onset of northern hemisphere glaciation. We have ice on Antarctica since 36 million years ago. And before that, we had a complete ice-free world, which the ocean was 6 degrees warmer. The atmosphere was of course, even much warmer, 10 to 12. And we had atmospheric CO2 concentrations of 1,000 to 2,000 ppm. So if we burn everything we have cheap, that's something like 5,000 gigatons of carbon, we can also accumulate something like 1,800 ppm of CO2. So if you're very cynical, you say, well, it happened before in Earth's history, 50 million years ago, but there was no complex planet Earth with 10 billion people. So it's awfully cynical, but that's the potential we have. So I'm one of those who thinks we should work on that, in particular as the kilowatt hour electricity from renewables is the cheapest we have since about 10 years. So we don't live up to the opportunities, and that's the cynical picture, right? We can reverse 50 years of Earth's history in 1 century. We don't want to do that. Back to science, policy advice. This is where a multilateral world that functions, and I think we matter, is just so important. No country alone can do anything about that climate crisis with other global crises. So this is where I was very proud on the process we had in Germany. Will be successful. Here, this is Christina representing Italy next to Marshall McNutt and the other presidents. I think we've written concise, short papers which did make an impression. At the end, the Ukraine war the Russian war against Ukraine dominated then the G7 meeting of the heads of our countries. But at least our text made it to the final document in a very elongate manner, and I hope it will continue that we do have those international collaboration. Right? The titles were, I think, very well picked. The Ocean and Crisis was one of the papers. The need for urgent international action, and the other one we call decarbonization. The case for urgent international action. We can't be more direct as this. We are, as a scientific community, we're not activists. Have to stay always polite and sane. But I think the proposals we make are very important. So for me, for example, and this is where we are far away in political realities, I don't think without the CO2 price we'll ever meet a climate target. Right? CO2 is garbage. Garbage needs to cost money. And without a CO2 price amongst the main emitters is something we will not meet. So I will at least try, for example, to talk to the Chinese Academy of Sciences. We can travel again. Just monolithic, just one thing, clean air and CO2 prices this year. It would be considered outstanding if we get anything done together. The United States colleagues have no option to talk to China. But I think this is an opportunity for us in Europe to at least engage in whatever discussion there could be, because we only have one atmosphere. And it just doesn't help to have disagreements on everything and anything, but get nothing done anymore. So I always found Don Quixote kind of a sympathetic figure. So let's just try. I come close to the end. We do this very often on national levels, but always with a European perspective on it. So I think the European Union is about the best thing we do have. We need to collaborate. We will never get completely independent on the energy system. So whatever we do, we propose in Germany is that take the European perspective into account. It wouldn't work otherwise. Not anyway. Sometimes to listen, we are still somewhat at the beginning is my feeling. What we do sometimes is for example, we have the most clicked report we have, that's we call it fact sheets on climate, where we also try to explain from basically laymen to high members of parliament, which very often still ask me, is it really that urgent? Does it matter? So we try very patient to explain and try to point out on our webpage to some of those processes. The other aspect, and I'm clearly out of time, which I'm just going to go over, genome editing is one of those aspects. I think also there without modern agriculture, but also combining probably the old knowledge of agriculture with modern techniques, we probably won't be able to feed everyone on planet Earth. There are big discussions in Europe. I feel many of the discussions move away from basically science-based approaches. Particularly the Green Party in Germany is having some of their old backbones there, which is completely uninformed, so it tries to be informative there. This is one of our efforts, and I think we have also some common efforts here to talk to the EU 27 when it comes to many of those crises described. So this is my last slide. I will not go through. The one backbone, which is really at my heart, and I'm 3 years president now, I have 2 more years to go, is we need to keep our independence. Right? In those difficult days with all those lobbying and whatever work, I think this is the most important point. We've learned to be faster, and what is at my heart is synchronizing with the international level, and I very much look forward, for example, to the joint statements we do this year at G7 in Japan, G20. We had over dinner with the conversation seems to be a little more difficult this year. India is the host, and then we all look forward to the next year leadership of Italy, and have the pleasure probably to all re-meet here in the Lincei. Mille grazie. Thank you very much for this kind invitation.